Good afternoon. This is Engineering Mechanics Statics. Once again, we're using the 5th edition of the Hibbler text. So we left off with working in three-dimensional space. Primarily using Cartesian vector notation. So picking up, let's start with working the problem out. So on page 50 of your text, problem 247. The problem asks us to determine the magnitude and the coordinate direction angles of the resultant force. All right, so let's see what we are. So let's draw our three-dimensional axes. Positive y, positive z, positive x-axis. We have a force F1. (400 newtons). We have a force on negative y-axis. We have a force F2. This angle here is 3-4-5 triangle. Our negative z axis. The angle between F1 and our z-axis degrees. F1 and the y-axis is 60 degrees. And F1 and the x-axis, I'll do it like this, is 45 degrees. X1's in the three-dimensional space. The angle the F2 makes with the XY plane and that between the x-axis is 20 degrees. So, in Cartesian vector notation, I'll write it up here. Get a different font color. Let's get a screen. Our F1, remember vector, both magnitude and direction. (400 newtons). So in the I direction or the X direction, the angle F1 makes with the x-axis, we said is 45 degrees. So then the leg we're concerned with then would be the cosine of that. And the direction or the unit vector I has to be applied. For the y direction component of F1, the angle between F1 and the y-axis is 60 degrees. And once again, the sense of F1 points in the positive y direction, so that's positive. And the cosine of that is the leg we want. That'd be the A, which is cosine, B leg, which is sine. So here we want the A leg. Unit vector J. And the sense of F1 points in the downward in the negative Z direction. And the angle of that force F1 makes in relation to the Z axis is also 60 degrees as well. And that would be the A leg once again. So cosine of that angle, 60-degree angle, gives us the negative Z component of that force F1. So it'd be minus cosine 60 degrees unit direction vector K. Force vector F2 is given as 125 newtons to magnitude. So we said the 3, 4, 5 triangle on the F2, utilizing that, we can get the XY plane component of F2, but we have to do a further angle analysis to get the actual X and Y components of F2. So the 4/5 leg, or the 4/5 ratio of the angle, 4/5, gives us the horizontal leg here, which brings us into the XY plane. So multiply that by 4/5. But we want the X and Y component. So they gave us the angle, the 20-degree angle, which allows us to then figure out how much of that force actually is applied in the X and Y directions specifically. So if I get the 4/5 ratio to get down the XY plane, I can do a further cosine or sine to get the X and Y component. So I will multiply that by cosine of 20 degrees to get the X component, which will be the A leg. And that's I direction. Now, that F2 sense is in the negative Y direction. So we have to subtract, once again, 4/5 ratio to get us in the XY plane. But we want the B leg, which would mean sine of 20. And that's J. And F2 points in the positive Z direction, so we'll plus this times. And in this case, we just need the 3/5. And can't forget about our K. So let's take that to the next page. Let's rewrite that. So we had F1, 400 times cosine of 45 degrees I, plus cosine of 60 degrees J, minus cosine of 60 degrees K. And this is in newtons. So F1, working that out, you get 282 0.8 I plus 200 J minus 200 K. We wrote force F2 as 125 times 4 over 5 to get us in XY plane times cosine of 20 degrees I minus 4 over 5 because the sense of F2 is in the negative Y direction times sine 20 degrees J plus 3/5 K. Solve that out. F2 gives us 93.9 I minus 34.2 J plus 75 K. So then our resultant force add F1 plus F2, I, J, and K components, you get 376.8 I plus 165.8 J minus 125 K newtons. Therefore, the magnitude of the resultant force, square root of the x component of the resultant force squared plus the square root of the y component of the resultant force squared plus the z component of the resultant force squared. We have 376.8 squared plus the 165.8 squared plus the minus 125 squared. The magnitude of the resultant force is 430 newtons. Then they also wanted the coordinate direction angles. Well, we defined this previously as cosine of angle alpha, which is the angle the resultant force makes in relation to the x-axis, will be the x component of the resultant force over the resultant force. Cosine of beta likewise follows the same pattern. Gamma so the x component of the resultant force is the 376.8, and we said the magnitude of the resultant force is 430 newtons. X component, y component, z component. Angle alpha is 28.9 degrees. Angle beta is 67.3 degrees. And the angle gamma is 107 degrees. Let's do another problem. Page 51 of the text. Problem 2-52. So here, pretty similar problem. They want us to find the magnitude and the coordinate direction angles of the resultant force. So drawing out the problem, first let's construct our axes. So we're dealing with three forces this time. We have a force F1, and they're telling us that it's in the XZ plane only. That's what they're saying. It's only in the XZ plane. The triangle or the angle here is simplified by 3, 4, 5 triangle. There's an F2 force. Not did that wrong. And they gave us the angle to get us in the XY plane. This angle is 60 degrees. They likewise then gave us the angle so a 60-degree angle to get us in the XY plane, and a subsequent 45-degree angle the XY plane angle makes between the X and the Y axes. Last but not, this is F2, 150 newtons. Last but not least, there's an F3 that is on the Z axis alone. Okay, let's get to work. So in Cartesian vector notation, magnitude and direction, my F1, like we said, is only in the XZ plane. So that's the 90 newtons. So the X component here will be the 4/5 ratio, Cartesian notation, and the Z will be the 3/5 ratio. And is in the sense of F1 is in the positive X and the positive Z direction. So it's plus. Okay. Solving that out. F2 is 150. Now, 150 newtons. For F2, we said that to get it in the XY plane, they gave us the 60-degree angle. So we have to do cosine of that to get the A leg here. So it's cosine of 60 degrees. And to get the X component, the I direction, that would then be the B leg of the 45-degree triangle, which would be sine I. And the sense of F2 extends in the positive Y direction, so it's plus. So once again, cosine 60 degrees to get us in the XY plane. But here it would be cosine of 45 degrees to get us on the Y. And for F2, to get the Z direction component, that is just the sine of the 60 degrees from the initial F2 projection. The sine of F2, as in the initial drawing, gives us the vertical, the zenith z direction component. So purely just a sign here. Solve that out, you get (53.03) plus 53 J plus 129.9 K newtons. And F3, that's purely on the Z axis. So it's in the K direction. So it's 200 K. The resultant force, 1, F2, F3. So adding those three forces we just came up with, you get 125.03 I plus 53.03 J plus 3 newtons. The magnitude of the resultant force is the square root of the x, y, and z components of the resultant force squared. So that'd be the 125 53.03 so the magnitude of the resultant force. Once again, the coordinate direction angles over the magnitude of the resultant force, 4 and 7. Angle alpha, after you do the inverse cosine. Cosine beta, the y component of the resultant force. Angle beta using the inverse cosine. And angle gamma So let's move on to section 2.7 in the text. Position vectors. So here we will talk about the concept of position vectors. And this is primarily dealing with just some good use of coordinates of different points. So a position vector is defined as a fixed vector which locates a point in space relative to another point. So for example, if we know the origin of an axis, we'll just say O, that has a coordinate of, say, three-dimensional space, 0, 0, 0. And we have some point P, and we'll give it the coordinates of, say, X, Y, Z. And if position vector R extends from the origin to point P, then R can be expressed in Cartesian vector form as remember, magnitude and direction now, in a more general sense, the position vector R may be directed not just from the origin to the point, but from any point A to point B in space. Let's show what we mean by that. So we have an axis, Z, X. If we have a point A here, we'll say this coordinates of A is XA, YA, ZA, which means to get from the origin to point A, you have to go some amount in the X direction, some amount in the Y direction, some amount in the Z direction to get to point A. That's the coordinates. And if we say we have a point B, given by some coordinates XB, YB, ZB, and if we direct position vectors from the origin to those points respectively, so you have a position vector R sub B to point B, position vector R sub A to point A, then the position vector or the fixed vector from point A to B, a different color, we'll just call it R. What does this look like? If we remember in the initial part of chapter 2, when we started covering it, we had some rules, triangle rule and parallelogram law about how to add vectors. And we had head to tail of the vectors, right? So here, we're connecting the tails by the common point, origin point, RA and vector RA and vector RB. So if you start at RA and you have from origin RA, that's tail to head, and then the tail of R starts at the head at A, then my resultant vector would be from the origin or the tail of RA to RB. It's pretty much the triangle rule. And here, the triangle rule, we said, hey, our result, I'll draw it out so it's clear to refresh you. So we had in the triangle rule, we had vector A, vector B, and we say, okay, let's add the resultant of A plus B. So we said vector A, tail to head, then vector B comes down. So then the resultant in the triangle rule is from the tail of A to the head of B. So in this case, our A is the origin to RA, so that vector. And then our head of RA is the vector R. So then in this case, our resultant is RB. So if we originally said R is equal to A plus B, in this case, we have RB, projecting vector R sub B, is equal to RA plus R. It's the same thing, you just look at it a little differently. So let's rewrite that on the next page. Make it look neater. So once again, let's try that again. The origin, we have some point A, given by the coordinates x, a, y, a, z, a. We have some point B, given by the coordinates x, b, y, b, z, b. If we extend position vectors from the origin R sub B, position vector A, we can then find a position vector relative from A to B. So not just from the origin, but from A to B itself. So let's do a different color again. We'll just call that position vector R. And what I was saying is, this is triangle rule all over again, where we have the resultant would be RB equals to RA plus R. So then R, RB minus RA. So expressing that in Cartesian form, position vector R is x, so the coordinates of position vector RB, so xb, I, magnitude and direction, yb, j, plus zb, k. Now remember, this is minus the position vector R sub A, I, j, k. So rearranging that, my position vector R between any 2 points is basically the difference in the coordinates. So it'll be xb minus xa, I, plus yb minus ya, j, plus zb minus za, k. So we're just taking the difference of the coordinates of the 2 points. It's pretty straightforward once you look at it. Let's work out a problem that exemplifies this. Let's turn to page 54 in the text. And this is example problem 210. So in this case, it says an elastic rubber band is attached to points A and B as shown in figure 235A. Determine its length and its direction measured from A towards B. So set it up. So we have a z-axis, y-axis, x-axis, and our negative z-axis here. We have a point B of the band. We have a point A here of the rubber band. So first, let's draw our position vector from A to B. Point A to point B. Right? And we said that the position vector is just subtracting the coordinates. So what are our coordinates of B? Well, coordinates of A, if we look on the diagram image A, from the origin to get to point A, in the positive x direction, they're showing you 1 meter. It says 1. In the y direction, do you go any direction? They're showing you that rectangle, they're showing you that the coordinates of A is in the xz plane, so there is no y component. So in the z direction, so 0 for y, in the z direction, is in the negative z direction, so that's a coordinate of -3. Likewise, for the coordinates of point B, to get from the origin to point B, in the x direction, you see you have to go in the negative x direction. So that's -2. In the y direction is positive. And it's showing that distance as +2. And it's in the positive z direction of 3 meters. Therefore, as we said, the position vector between A and B is the difference in the coordinates of point A and point B. So the position vector R is the difference in my XB minus my XA, my YB minus my YA, and my ZB minus my ZA in the IJK directions respectively. So my XB is -2, and my XA is 1. My YB is 2, and my YA is 0. My ZB is 3, and my ZA is -3. Okay. Simplifying that, rearranging it, you get your position vector is -2 minus 1 minus 3i. 2 minus 0 is +2j. And 3 minus a -3 is +6k. And therefore, the length of the rubber band is just the magnitude of the position vector r. So it's the square root of minus 3 meters squared plus 2 meters squared plus 6 meters squared, and you get 7 meters. Okay, so let's move on to some new stuff. Let's start working in chapter 3. We'll come back and do some problems in chapter 2 and a part of the review session. We'll do some more problems, but let's get into some new stuff. So chapter 3. Here we will start our studies of moments of a force, or force moments. So when a force is applied to a body, it will produce a tendency for the body to rotate about a point. Key word here is about a point. That's the terminology we'll be using when we're talking about moments, about a point. So this rotational, this tendency to rotate is either called a tendency of, say, a body to rotate about a point is sometimes termed torque, but in our text we'll be calling it moment of a force. So the magnitude of the moment is directly proportional to the magnitude of the applied force, F, and the perpendicular distance as we will determine moment arm, D. So the greater, I'll write it better. The greater the force, or the greater the moment arm, then the greater the moment or turning effect or rotating effect. Another term we're going to talk about here is line of action of a force or the force. We may exemplify, say, force, we say force F acts this way, but when considering moments, its line of action extends beyond the drawing. We're saying, what direction does that force, what direction is the force applied in? And a lot of times when figuring this out and working these problems, it's very helpful to, in your mind mentally or on a page, extend the line of action so you can understand how the force actually interacts with the body. It'll become clear once we work some problems. So the magnet, so we said, and let's draw it. So one more thing, our moment is a vector quantity, both magnitude and direction. And typically we say moment about a point, and typically we'll say moment about point O, but throughout your problems you can say point A, point B, it's just subscript. So, however, the magnitude of the moment so just the magnitude is the force times the perpendicular distance. And what we mean by that perpendicular distance is the distance from the point you're causing the rotation about and where the line of action of the force applies. And since moment is force times distance, units are either in Newton meters or pound force feet. So we have a force F being applied to some arm D that's some distance from point O. It causes, in this case, if the force is directed downward, it will cause a rotation about point O in a counterclockwise direction. So the moment arm, one more time, equals D, and that's the perpendicular distance from the applied force to the point, the origin, or the point of where we're applying the force to the body. Applied force line of action. Let's keep it that way. So once again, if our axis is at point O, given by this dot here, and we have a force applied some distance away, the perpendicular distance, what we call our moment arm, or perpendicular distance, D, allows us to calculate the tendency for that object to rotate about that point O. Now, typically, we express our moment since it can rotate. There's two directions it can rotate, either clockwise rotation versus counterclockwise rotation. And typically we set counterclockwise as the positive direction. And we typically write that as a plus sign and a counterclockwise arrow. So that's positive, which is saying any moments that are causing a counterclockwise rotation are positive. If the moments are causing a clockwise rotation, then we count them as negative. And since we said moments are vectors, just like our forces, we can have a resultant moment. Which is the algebraic sum of all the moments in a system. So counterclockwise being positive, the resultant lowercase or subscript r moment about point O is the sum of all my moments caused by forces in the system. So let's read that one more time. This side right here is termed as the moment about point O and in a counterclockwise direction. A moment about point O, or a moment about point A. The moment about some point. About mean is causing rotation about. So let's look at some problems so they'll become a little bit clearer. So on page 81, we have example 3.1. So for each case, determine the moment of the force about point O. In case A, point O, we have a perpendicular force here of 100 newtons The distance is 2 meters. Now we know this force is perpendicular due to they did not give us an angle or anything. So the moment this force, let's write it out so we can understand what we're saying. The moment the 100 Newton force causes about point O. That's the question. Now, we said the magnitude of the moment is a function of the force and the perpendicular distance. What is the perpendicular distance? That's always the first question to ask. What is the perpendicular distance from the applied force to the point O? In this case, we said it's pretty clear the 100 Newton force is at a perpendicular angle to point O and is given to us straightforward as 2 meters. So the magnitude of the moment about point O caused by the 100 Newton force is simply force times the perpendicular distance, which is 100 newtons times the 2 meters. Now, is that enough? No. Which direction is that 100 Newton force causing that body to rotate? Is it causing it to rotate in a clockwise direction or a counterclockwise direction? It's pushing down about a fixed point O, so it's causing it to rotate this way. So that's clockwise. Moments we have to notate which direction the rotation is going. All right, take a look at the next one, B. You have our origin. Distance 2 meters. Distance of 7.75 meters. And we have a force here of 50 newtons. Now we set our line of action. We want to know the perpendicular distance from the line of action to the point about which you're causing rotation. So remember I said we can we show our forces with an arrow, but the line of action of the force is helpful to extend it to understand what our perpendicular distance is. So what is the perpendicular distance between the line of action of the force, the 50 Newton force, and the point O? Is it 2 meters? No. If we extend that line of action from point O to here, the perpendicular distance is 0.75 meters. And remember, that's our perpendicular distance. So the moment caused by the 50 Newton force about point O is moment about point O, 50 newtons, times the perpendicular distance, 0.75 meters, you get 37.5 Newton meters. Now we said we have to display or say which direction is the rotation being caused. Now with the force applied here at the bottom of this body, it's causing a rotation this way, which is clockwise. Let's do C. I can draw better than that. We have our point O. This angle here is 30 degrees. And we have a 40-pound force, and the distance here is 2 feet. Okay, so first we said we extend our line of action of the force. So that's the line of action of the force. Now we want the perpendicular distance from the force line of, let's write it out. We want the perpendicular distance from the force's line of action to the point O. So, and it gave us the distance here as 4 feet. So using our right triangle rules, we know if this hypotenuse is 2 feet and the angle is 30 degrees, cosine gives us, of that angle, gives us this A leg here, cosine. So the perpendicular distance D will be 4 feet plus the 2 feet times cosine of 30 degrees. Therefore, our moment the 40-pound force causes about point O is the force times the perpendicular distance, 4 plus 2 cosine 30 degrees feet. It gives you 229 pound force feet. Let's look at problem D. We have a 60-pound force. Line of action of the 60-pound force. This angle here, 45 degrees. The length here, I was right inside here, 1 foot. So the first thing we want to know is, hey, what is our perpendicular distance between the line of action of the force and the point O. So in this case, different color. The A leg or the B leg? Which leg do we want? They gave us this angle here. The perpendicular distance from point O to that would be the B leg. So the hypotenuse is 1 foot. We want the B leg. So D is equal to the 1 times the sine of 45 degrees to give us the B leg, which would be the vertical leg, which gives us the perpendicular distance between the line of action of the force and point O. It's the vertical, the B leg. So 1 times sine of 45 feet. So the moment the force causes about point O is 60 pounds force and what direction is this force causing the rotation in? What you see is here is pulling it out, so it's more of a counterclockwise direction. Let's look at E. So with 7 kilonewton force here, let's extend the line of action. So the perpendicular distance between the line of action of the force and the point O is what? 4 meters minus 1 meters equals 3 meters equals to D, the perpendicular distance between the line of action of the force and the point O. So the moment the force causes about point O is the force times the perpendicular distance. Kilonewton meters. So then what direction is that force causing the body to rotate? It's pushing it, and about point O is our fixed point, is causing it to rotate counterclockwise about point O. Say counterclockwise So let's take a look at some problems. Let's look on page 96. Let's look at problem 3-4. The problem states, problem 3-4, determine the moment about point A of each of the three forces acting on the beam. So let's redraw the diagram. Okay, we got beam. This is point A. Point A is there. You have a F1, 375-pound force. We have a F2, that's 500-pound force. And it's at an angle. Is that what? 345. You have an F3, 160-pound force. They give you the distance here of 0.5 feet. They give you the angle, that is 30 degrees. The distance here is 8 feet. Distance here is 6 feet. And the distance here is 5 feet. I believe I got everything. All right, so the question says, determine the moment about point A for each of the three forces. Yeah. So remember, when writing it out, we said standard form counterclockwise is positive. So with counterclockwise being positive, the moment force 1, F1, makes about point A, I'm writing it out in this notation. The moment force F1 causes about point A. That's the way we're writing it. And that's the force times the perpendicular distance. The perpendicular distance between the force F1 and A is 8 feet. F1 is, they did not give us an angle, so we will assume that it's perfectly perpendicular to point A. So that's 375 pounds, and it's causing it to go down in a clockwise direction, right? It's forcing it down about point A. It's pushing it down, causing that body to want to rotate in a clockwise direction. And we said our counterclockwise is positive, so it'll be negative. So it's negative 375-pound force times the perpendicular distance, 8 feet. All right, F2. The moment force F2 causes about point A. The perpendicular distance is 8 feet and 6 feet. Okay, so F2 is coming at an angle. Would the A leg or the horizontal leg cause a moment about point A? The A leg will be right here, and this line of action goes through point A. If the force's line of action goes through the point, then there is no perpendicular distance, so then causes no moment. The vertical leg goes down, and it would have a perpendicular distance. So we would deal with the vertical leg, as we just said, the horizontal leg goes through point A, which will cause no rotation, so no moment. So we said our perpendicular distance is 8 plus 6, 14 feet. And we want the vertical leg. So that would be the, and once again, the F2 is causing down, pushing down. So it's causing a clockwise rotation, which is negative. So it'd be negative 500 pound force, because we're saying counterclockwise because it's positive moments, times our vertical leg component of that force, 4/5 ratio, times the perpendicular distance, 8 feet plus 6 feet. This gives you so last but not least, the moment force 3 causes about point A. So once again, our perpendicular distance. So here, if you notice, they gave us a point A, the beam has some thickness of 0.5 feet. Point A is on the top of the beam, and this force is applied at the bottom of the beam. So, and it's at an angle. So at this angle, the horizontal component, line of action, there is a perpendicular distance here. And the vertical component, line of action, there's a perpendicular distance here. So we have two, with the word about F3 from two perpendicular distances. So F3 is still applied at a downward direction. So it's still causing that F3 to, the body to want to rotate clockwise, which is negative. So we can't forget that. So in the downward direction, and it gave us the angle here of 30 degrees. So say 160 pound force. Now we want the vertical leg. Looking at this as the right triangle. The downward will be cosine. Cosine 30 degrees gives us the A leg, which is the vertical component here. So that's cosine of 30 degrees. And our perpendicular distance is what? 8 plus 6 plus 5. Perpendicular distance of the line of action of the vertical component is this total distance away. So it's 8 plus 6 plus 5, which is 19 feet. Now, the horizontal component, get a different color so it stands out. The horizontal component here, which would be the sine of 30, the B leg, right? That is causing it to rotate about point A in a counterclockwise direction, so positive. So here, which is at a new line, that's 160 pound force. And the horizontal, we said, is the B leg, so sine of 30 degrees. And what is our perpendicular distance from this line of action and point A is 0.5 feet. So here, the sum of those two components of the F3 force about point A, so the moment the F3 force causes about point A, add up both of these together, and we'll stop here in today's lecture and pick up next time. If there are any questions, please do not hesitate to email me. Be safe and continue to learn and work hard. Thank you.